Thank you, everybody, and thanks, Phil. Come sit in the front, don't hide. Right, so this is a collaboration. It's a complete collaboration between two institutions, the University of Nottingham with Phil, who's hiding behind me, and University of Oxford. But the people who have done this, I've put the acknowledgements first so that we don't forget, because they're actually the most important. So Dan Wilkinson, Ken Smith, Beth Phillipson, and Matthew, and I can't quite say his name properly, but Piasecki, who is in Phil's lab, and then Eleanor Jones, a grad student with Phil, and Lauren Kell, a grad student with me, have been doing the bulk of the work that we're going to talk to you about today. And this is a project that is built on, again, as the previous one, it's built on two previous UK spine funded projects where we were looking at the impact of DNA repair in aging, and Phil's lab were looking at the impact of rapamycin on muscles. So we've actually brought the two projects together to try and find out what rapamycin is doing in people to muscle and to immune health. Now, why rapamycin? Well, Jesus gave a wonderful introduction to why we need to do things about senescence, and he mentioned mTOR. And what we know, older people suffer from obviously multimorbidity, but one of the big things, hard to sit by COVID, and they also suffer massively from loss of muscle mass known as sarcopenia. And we know that mTOR is implicated in both those processes. So mTOR, a mechanistic target of rapamycin, so it sort of does what it says on the tin. Rapamycin targets mTOR. It's hyperactivated in aging and in cell senescence. And so this is actually the target of rapamycin, mTOR protein kinase, and that little blue blob there is the drug rapamycin bringing in another protein and altering the function of the mTOR kinase. And we know from the literature that rapamycin inhibits mTOR and does lots of beneficial things in aging. So it reduces features of cellular senescence. It increases mouse lifespan and health. And again, Jesus touched on that earlier. So if you feed rapamycin to middle-aged mice, they live on the human equivalent, an extra about 11 years. So that's quite a significant increase in life. But it's also a significant increase in health. So a reduction in a lot of age-related multimorbidities. So decrease in Alzheimer's symptoms and Parkinson's, improved cognitive function. So lots of good things happening with rapamycin late in life. And what has more recently been shown by Joan Manick in the States is that rapamycin or rapalogs, so equivalent mTOR inhibitors, improve older people's ability to respond to the flu vaccination. We'll hear more about vaccination and how to improve older people's vaccination responses from GARDA. But mTOR inhibitors also do that, and they reduce the severity of respiratory tract infections in older people. Jane's even got a small clinical trial in COVID now that's showing that people are protected from death or even serious illness from COVID using mTOR inhibitors. Now, the other issue is muscle and sarcopenia. And there's a slight paradox with rapamycin and mTOR in muscle. In young, fit, healthy people, you need mTOR activity, short-term acute mTOR activity to build muscle mass following exercise. And if you give rapamycin to young, fit, healthy people as they exercise, they don't actually increase protein synthesis in the muscle. So it's in a sense detrimental to the benefits of exercise in young people. But young muscle and old muscle are different. And this is the muscle in the thigh of a young man, a lot of lean muscle mass. And this is the thigh of a relatively healthy older man. And this is sarcopenia. This is muscle loss associated with age, or in my case, muscle loss associated with COVID and walking between the bedroom and the study for 1.5 years and not getting proper exercise. A lot of us is probably starting to look more like that than that. And that is a big problem. Muscle wastage is a major issue and a major cause of multimorbidities in older people. People tend to fall when they're frail, and it's a big, big problem. And so there is this dichotomy in older people. mTOR is chronically activated. It's not an acute thing in response to a short, sharp burst of exercise. It's on all the time and it's doing harm. And it seems to lead to muscle atrophy. And in old muscle, rapamycin treatment seems to improve muscle health. So that's in multiple different model systems. So in a premature aging syndrome, in a dystrophin model, in normally aging flies, you forget flies have muscles, but they do flap their wings, mice and dogs. And there's a big call in the literature now for use in humans. So this is where we're at. We're sticking it to humans, or rather Phil is putting it into humans. So the aim of the project, this is rapamycin, is oh, that's interesting. The aim of the project is threefold. So one of the key aims, of course, is the knowledge exchange and bringing people together and establishing new collaborations, doing things that people haven't done before. So we work on cell senescence, and we've got a new branch in immunosenescence. Phil works on metabolic biochemistry, muscle strength, and so we brought those things together. And obviously Phil's been working for a long time on mTOR in muscle as well. So we're bringing people together in new collaborations, and we have some specific experimental aims. The first of which is to find biomarkers for therapeutic monitoring. Now, biomarkers is a big bugbear, and obviously everyone in the world is looking for biomarkers, but so are we. And what we're looking for are biomarkers that if we give rapamycin to people, can we tell if there's been any beneficial outcome from that? So what I'm going to show you is some background information to, some development of assays prior to the clinical trial stuff, and then Phil's going to chip in and tell you about the clinical trial that's ongoing. And so what we've been doing is looking for things in the immune system that will tell us whether rapamycin is working. And we all know, and I've told you that mTOR goes up in cell senescence, and it leads to immune failure, increases risk of infection. That's a two-way street. Immune failure drives cell senescence, as does infection. So it's a vicious circle. And all of those result in the senescent cells kicking out loads of inflammatory markers. So Jesus talked about his screen for suppressors of the SAS, IL-6, IL-8. Well, those are inflammatory cytokines that are characteristic markers of chronic inflammaging. And so what we looked for as a baseline with Phil's clinical samples were cytokines in the blood of young people and old people. And because young and old aren't just two categories, we also looked at men and women because we do have very different immune systems. And again, that's quite hidden in the literature. And we want to disaggregate a lot of this data and work out what's going on a slightly more individual basis, rather than just you're young, you're old, you're over 65, you're not. So this is some very basic baseline data looking at different cytokines. This is using a fancy new platform we were lucky to have use of for 3 months. I won it in a competition Europe-wide, which was quite fun. It's a microfluidics platform that can do multiplex analysis of different cytokines. And just using these samples, we could distinguish on heat maps young females from old females in their cytokine patterns, young males from old males, young from old men and women. And so we could sort of disaggregate these data sets. What was quite interesting is young men are very inflammatory. Now, make of that what you will. But what we did find out is these inflammatory cytokines in the blood may be useful as age-specific and sex-specific markers of what might be going on in the innate immune system and inflammatory signaling. So another set of biomarkers, so that's what's floating around in the blood, secreted factors. And what we're also interested in is what happens to the cell-based component of the immune system, particularly the adaptive part of the immune system and the T cells. And you have very long-lived T cells in your body that can become senescent. And when they become senescent, the immune system isn't very good at dealing with new infections, hence COVID. And one of the features of senescent T cells is DNA damage. Now, DNA damage is a driver and a hallmark of aging. And this lovely review from Katja Simon, Katja is a co-supervisor of Lauren's project. They've pointed out just how significant DNA damage is in terms of being a hallmark of aging. And we know that DNA damage is also a driver of aging. People who have problems with DNA repair enzymes age quickly. And that's particularly seen in a previous spine project we're working with, Werner's syndrome. That's a DNA repair syndrome where there's a failure of DNA repair and people age very quickly. And then a really major paper, and I would recommend everybody read this, came out in 2021 in Nature, showing that aging of the immune system itself will drive whole body aging. So we think that looking at the immune system is absolutely core when we're tackling multimorbidity of aging. So what we're looking for in our patient samples is something called gamma H2AX. It's a marker of double-stranded break DNA damage. And it is a really important marker of double-stranded DNA breaks. And there's a nice paper there telling you that it's a useful biomarker for double-strand breaks. What we're asking, is it a biomarker that we can use to distinguish young immune systems that are working from older immune systems? And so what Lauren's been doing is collecting fresh human blood. So there's a little pot of human blood, separating it into the various different bits. So we've got the plasma, the white blood cells, and then all the other bits and pieces. Extracting those white blood cells, getting the T cells, activating them using cell surface, antibodies against cell surface, things that tell the T cells that they need to proliferate and activate, and then hitting them with a DNA damaging agent. And this is all setting up the baseline so we know that we can measure DNA damage in the immune T cells. So she's done recovery time courses, flow cytometry, looking at markers of DNA damage. And in the interest of time, I'll just zip through this stuff because this is FACS analysis, or rather fluorescence activated cell analysis rather than sorting. And you get graphs with loads of blobs on, and no one who hasn't done FACS knows what they mean. But essentially what we're doing is just looking at cells, so isolating lymphocytes, getting single cells out of that population. So this is called gating. You just put different borders around your cell populations and the machine will tell you what's what. And then you can look at their expression of various different features, and we can separate different types of T cells, CD4 cells and CD8 cells. And what Lauren's also done is looked for the presence of gamma H2AX in cells, plus or minus DNA damage. And so this extra red bit on the curve here is cells that have been exposed to a DNA damaging agent and are showing extra gamma H2AX, that marker of DNA damage. She's got data showing now that we can very clearly measure in FACS the amount of DNA damage in control cells versus damaged cells. We can look at the time course of repair because we think that older T cells actually fail in their DNA repair capacity. So she's got this data now for CD4s and CD8 T cells. It's a dose dependent response. So we know that what we're measuring is double-stranded DNA breaks. So we've got all the data sets now that give us a baseline where we can say we have a measure, a biomarker, if you like, of how T cells will respond to DNA damage. And what happens if we then expose those cells to rapamycin, the mTOR inhibitor? So we have the assay, treat those cells with rapamycin or the control vehicle. And what we find is that the zeaxanthin treatment does cause the double strand breaks we can measure, and the rapamycin treatment, even at relatively low doses, takes that right back down to control levels. So the rapamycin treatment is reducing the response to the DNA damage. Now, whether that's increasing DNA repair, which from the literature we think it might be, we haven't yet verified. So as our first experimental aim, identifying biomarkers of senescence or mTOR activity that are useful in therapeutic monitoring. We've got floating around cytokines that we may find useful, and DNA damage and repair capacity, the time it takes to repair, as a useful biomarker for senescence in immune T cells. And then the second part is to assess the effect of mTOR inhibitor rapamycin on immunosenescence and muscle parameters in older adults. And of course, if we're doing it in older adults, we need to have a clinical trial. And that is where Phil comes in. And I haven't left you much time, Phil, sorry.
I think I better use, can everyone hear me? So I don't know if I need this or not. So when this project was conceived, I looked around the literature around about in terms of what studies were happening in humans with regard to rapamycin, because obviously everyone knows the history of this. It's very long. For what I could see, there was a phase 2 trial, which was safety based. So a load of blood biochemistry and stuff that looks at, whether or not people are being harmed by treatment of rapamycin over 4 months. And they weren't. And so that was the basis of the duration of this particular trial. There is actually a trial funded by it's not a trial, an observational kind of science study in the US funded by the Impetus organization, which basically looks at gathering data from people taking rapamycin voluntarily. So there is a lot of people in the US who have decided to take it upon themselves to buy rapamycin and take it. So the idea is to gather some data from these individuals to see how this might be affecting them. But as it goes for controlled trials, there's not a lot out there that I'm aware of. This is actually on clinicaltrials.gov, and so you can find all the details there. One of the things that's also from the animal literature, which is quite impressive, if you look at it is longevity data mainly, but of course longevity, as we've heard, links to health span to a point. If you look at that data, it looks like basically transient treatment of rapamycin works as effectively as lifelong treatment. So there is kind of, even though you look at this as a snapshot and say it's like, 4 months treatment, it does seem that there is some hints of evidence that even short-term treatment can have really quite sustained effects for, I guess, kind of, not that well understood reasons at the moment. We hope to understand more about that from this trial. This is what the trial looks like, as you can see on the graph here. So we actually measure, a colleague in the back here, Dan Wilkinson, developed an assay mass spec to measure sirolimus, which is the active compound, which is a naturally occurring compound, by the way, that has basically been shown to have these effects. So it is a natural compound. It's worth pointing that out. You can see the blood concentrations shown here when we give people 1 milligram a day. Obviously, people would normally, it's immunosuppressive in its nature, and clinically it's used things like in organ rejection therapies. And it has been trialed in other areas, by the way, so things like leukemia to different or lack of effects or pro effects. But in terms of aging in humans, it's actually poorly defined still. So we achieve something like the dose is kind of, I guess it's largely, in a sense, unless you're a specialist in this area, it's largely irrelevant, but it gets into the bloodstream and it's sub-therapeutic dose. So we give less than what someone who was having who had an organ transplantation and was given an immunosuppressant alongside probably another drug as well called cyclosporine to limit any kind of organ rejection. This is what a protocol looks like. It's 4 months. We bring people in. I think the age is typically, I think we kind of have quite a liberal age. I think it's about over 55. We bring people in, screen them, and check their general health is okay, because of course we are giving it is a kind of drug trial in a sense. So we want to check that people are not at risk of any kind of adverse events that we might not know of. We randomize to either placebo or the drug. You can see the rest here. So they come in and they take this drug for 4 months. We take lots and lots of samples, and noticeably as well, Lynne mentioned about the interaction between muscle contraction or exercise and mTOR and aging. We know that, for example, exercise becomes less effective in the sense that the age muscle seems to be a little bit more resistant to the normal growth or anabolic effects of exercise. So we're interested in, if we're going to give rapamycin and we increase health, that's great. But if it has a negative impact upon muscle contraction, then that's bad. So we want to understand more about that. So they actually come in, do unilateral exercise, so just one leg. And what happens with muscle is that even though there are systemic factors that respond to exercise, what actually happens is that, that one leg will actually grow. So the other leg doesn't. So it's quite weird. You can kind of imagine someone sort of walking around in circles because they've got one big leg and one not so big leg. So we study the interaction between exercise, age, and mTOR in that respect. We take loads of I won't bore with the measurements, but we get lots of functional metabolic readouts of how this affects muscle health, and also obviously the one of the key things here is through UK Spine we've been able to interact with Lynne to try and understand. I'm sure there's lots of information around organ crosstalk. One of which is very much the immune system to lots of other organ systems that include muscle. So we're interested in the interaction between, the aging of the immune system and aging of the musculoskeletal system. So I think with that, I'll probably leave that there. I'd happily take any questions.
Thank you very much to Lynne and Phil. So we have 5 minutes of wrong footage running.
Just in terms of assessments for muscle strength, there's a couple of things I've come across that are indicators, particularly of good healthy muscle aging. One is grip strength, and they're trying to incorporate that in clinics for older people to actually, handshake with them, perhaps, on entry, get an assessment of their grip strength. But the other thing I recently read about was the ability or inability to stand on one leg for more than 10 seconds was a good indicator of actually advanced morbidity and mortality. So just a couple of comments if you weren't aware of them. So it looks as though you are. Thanks.
Yeah, absolutely. Thank you for that. Yeah, so from a hand grip perspective, we always take hand grip strength. One thing you find with hand grip strength is brilliant from an epidemiological perspective. So if you look at relationships to hand grip strength and other things, it's very robust. If you look at response to interventions, especially which doesn't involve the forearm, then it's not so much so, but nonetheless, it's, of course, we do take that. We actually take a combined measurement of physical functioning as it pertains to daily living. So we use the short physical performance battery test, for example, which involves rising from a chair. So really, not sophisticated measures, but the most important measures of that. One of the caveats here is simply that we tend to recruit people, and again, this has been raised already today, we're not at this stage recruiting people who have functional limitations. Should it come to that, because what you find is that when you do these tests, that most people pass with flying colours, and so any intervention has no effect. But in the future, of course, the aim is to go into more frail populations. Thank you.
So one question down here.
Thanks for the great presentation. The question for Phil, I just wondering about the how we say that, like biopsy of the tissue or of the muscles. Is it coming from the same muscles? Because I'm not sure. I mean, if we have the same effect from all over the body,
yeah,
it's harmful for the people to have it from the same.
Yeah, good question. So no, we can't. Of course, I mean, muscles are homogeneous in a sense, but very heterogeneous in another sense, right? From a cellular perspective. So we take it from the thigh, so the vastus lateralis, which is the most commonly biopsied muscle. It means you can effectively look across, you can draw lines through other studies in that using those techniques. The other thing I didn't mention is we also take muscle satellite cells. So we actually pull out the stems, the muscle stem cells, which I think Jesus mentioned about earlier, the CD56 positive cells. So we have a bank of those. So we're able to look at, in the future, theoretically, how in vivo rapamycin exposure affects muscle stem cell function.
So we've got time for two more questions. I've seen one hand over there and then one down here.
Hi, thanks for a really nice talk. My question is along similar lines. It relates to resistance training. Have you considered comparing this protocol to purely a resistance training intervention?
So, sorry, your question exactly.
So this protocol, have you considered comparing this to a group that would be purely on a resistance training protocol?
Yeah, so all we have here is a placebo versus the Rapamycin drug. So what we do have is we're able to discern whether or not the drug has any negative or positive impacts in interaction with resistance exercise. In the past, we've done lots of work on, how age impacts the general response to resistance training. But in this one, what we're really, I guess we're more concerned of causing harm with the interaction with muscle contraction. So what I'm not necessarily expecting some giant muscles, but I'm kind of hoping that we don't have a negative impact upon the training induced or contract, because that's so important to day-to-day maintenance of muscle mass, because everyone sees resistance training as, lifting weights or exercise, but actually any kind of loading is positive to the muscle. So we must understand the drug interaction between, even ambulation, right? And this is a kind of, I guess an extreme form of trying to understand that, if that makes sense.
Thank you. So one last question over here.
Thank you. Thank you both for a really interesting presentation. I've got a double part question, if you don't mind. It's one's about the target, one's about the Rapamycin. First of all, just intrigued, Lynne, about what's switching mTOR during the aging process to one where it's turning on constitutively in the aging muscle. Is it about your lifestyle, or is it something genetic? And then the second one is about the Rapamycin and the what you've shown there, Phil, in terms of the therapeutic dosing. And are you confident about target engagement and you know, are you actually covering the target for sufficient length of time?
Cool question on both counts. As far as I'm aware, I've been speaking with people who work on sarcopenia, so there's a big group up in Newcastle. Obviously, Phil's been working on muscle for donkey's years, sorry. And there isn't such a thing as a switch. You don't suddenly get to the age of 65 and you go from, oh, my muscles work with exercise and mTOR is good, and then suddenly I hit my 65th birthday and it's the other way around. It's a very gradual process. It appears potentially to correlate with the presence of senescent cells and potentially a senescent SASP. Phil's mentioned about the satellite cells, and we were planning jointly to look at senescence in the satellite cells. There's a lot of data in those that satellite cells go quiescent, which is good, but if they're quiescent for a bit too long, then they can actually go through a quiescence-induced sort of senescence. So there's a lot known about those pathways. So the couch potatoes, sorry, I'm not very PC. The people who do not undertake regular active exercise tend to age more quickly. Potentially their muscles will undergo that TOR transition from acute is good to on all the time chronic, because they've undergone a process of senescence. But the literature, as far as I can tell, is particularly on human, very, very not out there yet. So I can't really answer your question, but it's not a switch. It's a gradual process. And exercise, as Janet will tell you, exercise will maintain muscle health for an awful long time, and it's anti-inflammatory. So yeah, I think exercise per se, as well as mTOR inhibitors, are probably going to be good for our biomarkers. Phil, target engagement.
Yeah, no, I mean, sorry, target engagement. So no, so in terms of the cell signaling side of things, mTOR is a complicated little beast in terms of, it's got so many partners, right, that are negatively and positively regulating it. And I don't think in humans, all I can say is that when we take proxy readouts, so if we look downstream, we see it's up, and that's in humans. We see it in mice and rats too. What the precise mechanisms of that are, I still think are elusive. Sorry, was there a second question? Apologies.
The Rapamycin actually.
Yeah. Well, we've got the biopsies, actually. Great question. Of course, the proxy readout will be suppression of TOR signaling. We haven't done that yet. We're hopeful. We think that the dose is reasonable. We're trying to go in between the sort of therapeutic dose and again, this was based on that phase 2 trial showing safety. So we felt it was reasonable to go with that dose and not go beyond that, and also not go beyond the duration, and hopefully generate some data to sort of move forward with.
In terms of target engagement for the immune system, it's about the right sort of dose that was used in the everolimus RAD 001 trial for the flu vaccination. So on the immune system, yes, target engagement, muscle potentially, and there's some work on satellite cells in vitro from Phil's data bank that suggests that is the right sort of dosing. So until we've got what we need to do is collect all of the data and process them, so we don't have the batch to batch variability that was a question earlier. So a lot of this is still very much work in progress, and we're doing all the sort of biochemistry, the proteomics, the metabolomics, the transcriptomics at the end when we've got all of the data, all of the samples together. Yeah. Okay.
Thank you very much. So thank you very much to Lynne and Phil.